Let's take a look at example number 3 now, and we're still going to be using this definition of continuity here to answer the question here in example 3. This question says, prove that the function f of x, oh gosh, which is again even more complicated than the one before, show that this is actually a continuous function at x equals 5. Okay, so again, it can be helpful to try to think about kind of like a mock picture of what this function might look like. So I can see here that this function has two different pieces, kind of like the function before. Except here, I recognize that one of my pieces was actually just a single dot, whereas in this hypothetical picture, I can see that at the value of 5, I have a blue piece that is going to have a dot and extend off to the right, and then I have a red piece that is going to have a hole and extend off to the left. Now again, I don't know if this is exactly what the picture looks like. In fact, it's probably not what the picture looks like, but it helps me see that there are red and blue pieces here and where those pieces are pictured. If this function is going to be continuous, it'll actually need to be the case that this red open hole here will actually perfectly form around this blue dot, and that would allow the graph to stay connected. But in order to figure this out, to see if that happens, we're going to go ahead and calculate these two things just like we did in the last question. Okay, so let's go ahead and start by starting to think about the limit. Okay, so I'll start by saying the same thing, except that we note that in order to calculate the limit of f of x, in this case as x approaches 5, we need to check the limit from both sides. Notice in the previous example, both sides of the value 1 were blue pieces, so I could just calculate the limit of the blue stuff. However, in this case, on either side of 5, I have different portions of the function, and so I need to check the limit from both sides to make sure that they come out the same, so that way I can actually see if the limit exists. So let's go ahead and actually do that. I'll start by saying we see that if I do the limit as x approaches 5 from the left, that would be using, well, the left part of my function is the red part. So that would be doing the limit as x approaches 5 on the red. But notice that that red piece there is just a polynomial. So I can use direct substitution and just evaluate at the value of 5. So this is going to be 10 minus 7 times 5, or 10 minus 35, which is negative 25. Okay, so that's the limit from the left. What about the limit from the right? Well, if I check the limit from the right side, that would be using the blue portion of the picture. So my limit as x approaches 5 from the right would require that I use x squared over my 4 minus x. But again, that's a rational function, so again, I can just use direct substitution. And I'm going to get 25 over 4 minus 5. That's going to be negative 25. Okay, great. So since the limit from the left and the limit from the right came out the same, I can go ahead, put these two things together, and state that the limit as x approaches 5 of f of x is equal to negative 25. Now notice I haven't actually answered the question yet really at all, because in order to show that my function's continuous, I have to calculate the limit, which I just did, and I still have to calculate the y value and see if they produce the same number. And I haven't yet computed the y value. So let's also compute that. I'll say, also, if I wanted to just compute f of 5 directly, well, let's see, if I was plugging in the number 5, would that require me to use the top blue piece or the bottom red piece? Well, it says up here that if x is greater than or equal to 5, I should use the top. So that would require that I actually use this formula to compute f of 5. And like we just saw, that's going to give me the value of negative 25. So the limit is negative 25, the y value is negative 25, and so I can conclude that the limit as x approaches 5 for my function is equal to f of 5. They both produce the same value. And so f of x is indeed continuous at x equals 5. So it's really important to note that in this example and in the last one, we've consistently checked both of these values and compared if they were the same value. And this is what you would have to do on every single question if you wanted to figure out if a function was continuous at a point. That's it. So you can see how important knowing this rigorous definition actually is. You have to know this. If you don't know this definition here, there's no way to answer questions in this section successfully.